Hi folks, this is part 3 in the car generator series. In part 1 we took apart the Harbor Freight generator that had thrown a rod, and we mounted a plate to the front of the generator to hold the bearing, and then we built a clutch and a pulley. In part 2 we actually physically mounted it in the car. Here in part 3 we are building an electronic circuit to control the throttle to hold the generator at 3600 RPM. That's the speed it needs to run to make 60 cycle AC current. And we're using the cruise control actuator in the Toyota Sienna to adjust the throttle. So in a moment I'm going to show you how that works. We'll start it up. We'll turn on the control module. It'll come up to 60 cycles with no load, and then we'll put a couple of loads on it. I've got an angle grinder that pulls about 5 amps or so, and I've got a 1500 watt space heater. So try both of those and we'll see how things work. Okay, let's take a look at the components I used. First of all, we have the cruise control actuator, and the way this thing works is it has a clutch and then it has a motor with a worm drive on it that moves this arm. The way you use it is you apply 12 volts to the clutch. You'll hear this click. And then once you've applied that voltage to the clutch, the actuator will move in one direction or the other depending on the polarity of your input to the worm drive. And there are limit switches so that when it hits the end of its run, it shuts off. It doesn't wreck the motor. So that's how this servo actuator works. Now, to drive this, one uses a device called an H-Bridge. And this is basically 4 transistors in a bridge configuration with the motor at the center. So if you turn on these 2 transistors, voltage flows through the H in this direction. If you turn on these 2 transistors, voltage flows through the H in the opposite direction. So the motor turns either clockwise or counterclockwise, depending on the signals you give this device. And the signals you give this device come in on these pins, and they're an enable signal or a PWM signal, clockwise, counterclockwise, and this is a 2-channel bridge. So I'll be connecting this channel to the clutch and this channel to the actual servo. And then the signals that come into these pins from the Arduino microcontroller will actually control whether the servo's engaged and which way it goes. In addition, I've added this liquid crystal screen to help me debug and to know what's going on when I'm operating the control circuit. And this takes a simple supply voltage ground, and then there's a data and a clock pin which come from the Arduino. Here's the circuit diagram for all of these components together. Start with a voltage regulator. This is a 12-volt voltage regulator. Since we're in an automotive environment, volts can be as high as 16 volts. So I want to keep everything in the circuit at 12 volts. So I've got an LM7812 here that provides my 12-volt supply. The signal from the generator, the 60 cycle signal, comes from this wall wart transformer. It's 120 volts in, 9 volts AC out. I have a voltage dividing bridge here, which will reduce that to about 4.5 volts. Then we rectify it. So whereas we have sine wave coming in here, we have a half sine wave coming out here to reduce noise and to make sure that we never put more than 5 volts into our comparator chip. This is an LM311. We have a 4.7 volt Zener diode. This will make sure that if this voltage ever goes above 4.7 volts, this will short it to ground, because we want to make sure we don't blow up this chip. This is a comparator. So what a comparator does is looks at 2 incoming voltages. If the voltage on this leg is higher than the voltage on this leg, then the output is a logical 1. In this case, it's going to be a full 12 volts. If the voltage on this leg is higher than the voltage on this leg, the output is a logical 0, or 0 volts. And that crossing point is set by this potentiometer. This is a 20K potentiometer between the 12 volt rail and ground, and it's set for about 6 volts. So when this waveform crosses that 6 volt point, this turns on, and when it goes below, this turns off, and that means we get a nice square wave output from our comparator, and that's what the Arduino is going to look for to determine our frequency. Again, this signal is a plus 12 volt signal, and I want to make sure that I never give my Arduino more than 5 volts. So I have a resistor bridge here and another 4.7 volt Zener to clamp this voltage so that the voltage can never go over 5 volts. And that I feed into pin D2 on the Arduino. That's pretty much the only input the Arduino needs. We're just looking at frequency, and we are moving our actuator forward if the frequency is too low and backwards if the frequency is too high. The Arduino has outputs that feed the H-Bridge. This is our motor driver. They are PWM, forward, reverse, and PWM. I have wired this for PWM, and I used the L298N library that supports PWM, but what I found was that to get the smallest increment that this actuator can produce, what I needed to do was hit it with about 7 milliseconds at full voltage. I could get slightly smaller increments if I used the PWM function to slow it down, but not much, and its behavior was a little inconsistent. So although I've implemented PWM by wiring these outer pins, and I have implemented in the code, I don't actually use it. I give full voltage to the servo motor for each step. But that's what these pins here are for PWM. So if you wanted to do this without using that function, you could leave the jumpers on these 2 pins and use the library that the part of the library, the L298N library that doesn't support PWM, and that's fine. In addition, the second channel, the B channel, I never use the counterclockwise pin because that would reverse the voltage on this, and there is a diode across the clutch in the servo that would blow up if I ever gave it backwards voltage. So I never use this. This pin never goes high with my code. So when we're functioning, this pin goes high, that engages the clutch, and then one or the other of these pins go high, and that turns it clockwise or counterclockwise. The connection to the LCD module is pretty straightforward. It gets ground, and VCC, in this case, plus is 5 volts. So we use the 5 volt out from the Arduino to power the LCD module. And then there's a data and a clock pin that come from the Arduino. And that's pretty much all the electronics. Let's now take a look at the actual electronics, and I'll show you the waveforms and how this comparator converts the sine wave into a square wave. Here's our actual circuit. I'll power it up. It initializes and starts running, and you see we have no input, so I'm going to plug our transformer in to the house voltage, and you see now we're reading a frequency. Let's open this up. Okay, here's our circuit operating. This is the input from the transformer, and you can see it's a nice sine wave. And we feed it through our little half-wave rectifier. We get our modified sine wave. That feeds into the comparator, and then out of the comparator, we get this nice square wave, which is what the Arduino needs to count the frequency. Looking at our production circuit here, These are the resistor networks that feed the comparator, our Arduino, the potentiometer that sets the input voltage for our comparator. This is the LM7812 voltage regulator, our H-bridge with connections to the clutch and to the worm drive. It gets main power, and then it takes signals from the Arduinos here. And the Arduino is connected with its data line and clock line to the LCD. The 5-volt regulator on the Arduino also powers the LCD, and that's pretty much it for the circuitry.
Okay, let's take a quick look at our Arduino code. This is not intended to be any sort of Arduino tutorial. In fact, this is the first time that I've used an Arduino on a project. I've implemented them in 3D printers, but I've never done any coding for them. And it's been 30 years since I did any C coding. So this may be a little bit rough, but I'll walk you through what I did here. It's a fairly simple program. So first thing I do is load the L298N library. This is the library for driving that dual channel H-bridge. And if you're using both channels, you'll need to load the X2 version of it. Then I load the liquid crystal library. I found some code online, and I'll put a link to the example in the comments. And this is the code that I used for the frequency measuring portion of the program. And that's what these variable assignments are. Oh, up here, once you load the libraries, you need to instantiate the objects so that this basically just gives the program a handle so that you can use them, and that's what happens here. And like I said, these are variables used in the subroutine that measures the frequency. So basically, we initialize the serial LCD, we set our servo speeds, and like I said before, I didn't use the PWM. If you did want a slower servo speed here, you could use something less than 255. 255 basically means full on here. This is the interrupt routine. This is what does the capture of the pulses to measure the frequency. And I will let you look at the example that I link in the comments for the details of how that works. The original author can do a much better job explaining it than I can. So first thing we do is we get our frequency. We see how fast the generator is turning. If that frequency is less than 25 or over 100 hertz, we don't do anything. Something's wrong. If the frequency is over 25 hertz but under 40 hertz, then we need to cycle pretty quickly to take up the slack in the servo mechanism. So we set our cycle time to 150 milliseconds. If the frequency is above 40 hertz, we set our cycle time to about 2 seconds. That seems to be a good sweet spot for letting the generator settle in. Then we move our servo forward. We check our frequency. If we're under 59, we need to move forward. If we're over 61, we need to move backward. Otherwise, we stay still. In each case, I print out to the LCD what the current action is along with the frequency. And then we just loop through this process over and over and over again. If we ever go outside the bounds, if something happens to the generator so it's not producing power, or if something happens such that the engine revs high enough so that it goes over 100 hertz, we stop the servo, and so servo B is the clutch. So stopping servo B releases the clutch and the spring closes the servo. This is the interrupt handler that senses the pulses. Get freak is the routine that counts the pulses to get the frequency. And that's the end of our program. It's pretty straightforward.
So why don't I put this back together, put it back in the car, and I'll show you it in action. Okay, I've got one camera focused on the controller and the other camera on the actuator. I'm going to start the car now. Currently, the generator is turned off, so there is no frequency on the meter. I'm now going to turn on the generator. You'll see the actuator moving fairly quickly. If the frequency is below 40 hertz, there's a cycle time of 200 milliseconds. Once the frequency gets close to 60 hertz, the cycle time is about 2 seconds. The circuit gets close to 60 hertz fairly quickly, and then it takes about 20 or 30 seconds to hunt back and forth until it zeroes in on a good solid 60 hertz. The tolerance is actually anywhere from 59 to 61. The bottom line is the cruise control actuator doesn't have enough resolution to really dial in the speed quickly. So it has to move forward and back a couple of times, and because of the spring tension on it, it moves forward a little bit less than it moves back. So it advances the speed, it falls back a little further than it advances again, and ultimately zeroes in on a good speed. So now we're going to go ahead and we're going to add the 1500 watt resistance heater. And now the angle grinder. Now you can see with a variable load like the angle grinder, it does do a lot more hunting back and forth. However, with the angle grinder, that's not a problem. There's a voltage regulator in the generator that continuously provides the 120 volts. And because the angle grinder is a universal motor, it doesn't care what the frequency is. It'll run on DC. If I were running sensitive electronics, I would hesitate to run the angle grinder with them. And that's a wrap for the generator project. In the comments, you'll find links to a lot of the components that I've used, and also references to some of the web pages where I found the example code for programming the Arduino. This one was a bit of a journey. I didn't expect to be using a microcontroller. My original intent was to do this with operational amplifiers. One of my very first jobs was designing an op-amp-based control for an automotive radiator cooling fan, and I thought I could do it here, but the key thing was the resolution and the response time of that servo. It made it very difficult to properly compensate for the hysteresis of the system with operational amplifiers. I tried all sorts of things, some kind of nutty. I built a more precise actuator from old cordless drill and an IKEA shelf bracket. It worked, but nowhere near accurate enough to dial in the frequency. So I had to learn about Arduino microcontrollers, which is not a bad thing because in a future project I am going to be using an Arduino to control an H-bridge, to control a servo motor that will move the tiller on my sailboat. I'm building a autopilot based on the open plotter system. So stay tuned for that. This is Jake von Slatt. I'll see you next time.